There is a place beneath your feet where the weight of an entire planet presses inward with such force that iron loses the ability to melt. The center of the Earth exists at pressures we have never touched, never measured directly, and almost certainly never will. We know these pressures only through mathematics and inference, through the behavior of seismic waves passing through regions no human instrument has ever visited. What we call solid ground is only the thinnest skin, floating above an interior shaped entirely by accumulation, layer upon layer of mass bearing down across billions of years, creating conditions so extreme that the rules governing matter at the surface no longer apply. Pressure, in its most basic form, is nothing more than weight distributed across space. Stand on solid ground and you are experiencing it. The accumulated mass of atmosphere pressing down from above, roughly 15 pounds on every square inch of your body, a constant companion so familiar that your nervous system long ago learned to ignore it entirely. You do not feel this weight because you were born into it, because every cell in your body developed under its influence, because the fluids inside you push outward with equal force. The air around you is not weightless. It has mass, and that mass extends upward for miles, thinning gradually but never disappearing. A column of gas molecules pulled toward Earth's center by gravity, each layer bearing the weight of everything above it. At sea level, this creates a pressure we use as our reference point, our baseline for understanding what it means when we say the word normal. But normal is only a starting place. It is the pressure of the surface, the pressure of breath and blood and weather, the pressure that shaped the biology of every organism that crawled out of the ocean or flew through open sky. It is not the pressure of depth. Descend into the ocean and pressure begins to accumulate in a way the human body can detect. For every 10 meters you sink beneath the surface, the pressure increases by roughly 1 atmosphere, the equivalent of adding another 15 pounds per square inch to every part of your body. At 30 meters, recreational divers begin to approach the edge of what untrained lungs can manage without difficulty. At 100 meters, technical divers breathe gas mixtures carefully calibrated to prevent nitrogen from dissolving into tissues in dangerous concentrations. The ocean is patient about enforcing its rules. It does not crush suddenly. It simply adds weight incrementally, and the deeper you go, the more your body must resist the slow inward press of water that surrounds you on all sides. This is hydrostatic pressure, the pressure exerted by a fluid at rest, determined solely by the weight of the fluid above and the strength of gravity pulling it downward. It is predictable, linear, and utterly indifferent to whether you are prepared for it. At the bottom of the Mariana Trench, nearly 11 kilometers below the surface, the pressure exceeds 1,000 atmospheres. A human body unprotected at that depth would not explode outward, as some imagine, but would instead experience rapid and catastrophic compression. Airspaces collapsing, gases dissolving into blood, tissues compressed beyond the point where biological structures can maintain their integrity. No human has ever been there without a pressure vessel, and likely none ever will. But the ocean, vast as it is, represents only the Shah. The crust is not uniform in its resistance. Some rocks yield more readily than others, some compress into denser forms, some retain tiny pockets of trapped fluid or gas that existed when the material first solidified. Granite, the foundation of continents, is relatively light as rocks go, composed of minerals that formed as molten material cooled slowly beneath the surface. It is strong in the sense that it resists fracture, but under sustained pressure it behaves differently than it does at the surface. It does not snap or shatter. Instead, it adjusts. The mineral grains within it shift position incrementally, sliding past one another along boundaries too small to see, rearranging themselves into configurations that occupy slightly less space. This is not a fast process. It happens over timescales that make human observation impossible. You cannot watch granite compress. You can only infer it from the structure of rocks brought to the surface by tectonic forces, rocks that once existed deep within the crust and now bear the evidence of their history written into their crystalline fabric. Geologists call these deformation features, and they are everywhere once you know how to read them. Elongated mineral grains, foliated textures, bands of darker and lighter material aligned in directions that reveal the stress fields that shape them. The deeper you go, the more these features appear, until at a certain depth the rocks themselves begin to transition into forms that no longer resemble anything familiar from the surface. The boundary between crust and mantle is not a sharp line. It is a transition zone, a region where the composition and behavior of rock change gradually as pressure increases. The crust, light and brittle near the surface, gives way to the mantle, which is denser, hotter, and under such immense pressure that its mineral structures can no longer remain stable in the forms they held closer to the surface. This boundary is called the Mohorovičić discontinuity, named after the Croatian seismologist who first detected it by observing how seismic waves change velocity as they pass from crust into mantle. The waves do not stop. They do not reflect back entirely. They simply speed up because the material they are traveling through has become denser and more rigid, compressed into a state where sound moves faster through it than it does through the rock above. The Moho, as it is often called, lies roughly 30 to 50 kilometers beneath continents, shallower beneath oceans where the crust is thinner. It is not a place you can visit. It is not a surface you can touch. It is simply a depth at which the cumulative pressure has reached a point where one type of material becomes another, where the minerals that make up crustal rock are no longer thermodynamically stable and are replaced by minerals that can exist only under greater confinement. Olivine is the dominant mineral of the upper mantle, a dense silicate that forms at high temperatures and pressures in conditions where granite could not persist. It is green when pure, though impurities often darken it, and it crystallizes in structures that pack atoms more tightly than the minerals of the crust. Olivine is what basalt becomes when pressure and heat strip away the lighter elements, when the material is forced into configurations that minimize volume and maximize density. It is stable across a broad range of depths, from the Moho down to roughly 400 kilometers, and throughout this region the pressure continues to rise in direct proportion to the weight of everything above. At 100 kilometers depth, the pressure exceeds 30,000 atmospheres. At 200 kilometers, it doubles again. The rock at these depths is not molten despite the heat, because pressure raises the melting point of minerals far beyond what temperature alone can achieve. The mantle flows, but it flows as a solid deforming over millions of years in response to thermal currents and gravitational forces, moving at rates measured in centimeters per year, carrying continents on its surface like debris floating on a slow river. This is convection, but not the convection of boiling water or rising air. It is the convection of solid rock moving through solid rock, driven by temperature differences too subtle to feel and pressure gradients too vast to comprehend. Heat generated by radioactive decay deep within the earth rises slowly through the mantle, warming the material just enough to make it slightly less dense than the rock around it, and that small difference in density is sufficient over geologic time to cause motion. The heated rock rises, the cooler rock sinks, and the entire mantle circulates in patterns that take hundreds of millions of years to complete one full cycle. This motion is what drives plate tectonics, what opens ocean basins and closes them again, what builds mountains and wears them down. But it is invisible from the surface, perceptible only through its effects, through the motion of continents measured by GPS satellites, through the earthquakes that mark the boundaries where one plate grinds past another. The mantle moves because pressure allows it to move, because the atoms within olivine and its companion minerals are packed tightly enough that they can slide past one another without breaking the bonds that hold the crystal structure together. This is not fragility. It is a kind of strength that only exists under confinement, a plasticity born from the inability to expand, lowest boundary of depth. The true pressure of Earth begins where water ends and solid rock takes over. The weight of seawater is immense, but it is still only water. Molecules loosely bound, free to flow and shift. Rock is different. Rock is mass in its most patient form, piled layer upon layer across geologic time, each stratum adding its weight to everything below. The continental crust beneath your feet extends downward for 30 or 40 kilometers on average. Thicker beneath mountains, thinner beneath ocean basins, composed mostly of granite and sedimentary formations that bear the history of erosion and deposition across hundreds of millions of years. These rocks are not static, They are compressed by everything above them, held in place by pressure that increases with every meter of descent. The crust is Earth's skin, but it is not a light skin. It is a dense, layered accumulation of mineral matter, and even at shallow depths the pressure begins to exceed anything a human could survive. At 10 kilometers down, a depth we have never drilled through completely, the pressure is roughly 3,000 atmospheres, enough to alter the physical properties of most materials, enough to make water remain liquid well above its normal boiling point, enough to compress rock until its internal structure begins to shift. This is where metaphor begins to fail, or at least becomes inadequate. We speak of pressure as if it were a squeezing hand, as if it acted from outside. But deep inside the Earth, pressure is omnidirectional. It does not push from one side. It presses inward from all directions simultaneously, a radial force distributed evenly across every surface, every grain, every atomic bond. Rock under pressure does not crumble the way surface rock does when struck or stressed. Instead, it deforms slowly, flowing over geologic timescales like an extraordinarily viscous fluid, creeping and shifting in response to forces that act continuously across millions of years. This is not the pressure of collision or impact. It is the pressure of accumulation, the patient arithmetic of mass and gravity summed across planetary dimensions. And it is only beginning. The crust is not uniform in its resistance. Some rocks yield more readily than others. Some compress into denser forms. Some retain tiny pockets of trapped fluid or gas that existed when the material first solidified. Granite, the foundation of continents, is relatively light as rocks go, composed of minerals that formed as molten material cooled slowly beneath the surface. It is strong in the sense that it resists fracture, but under sustained pressure it behaves differently than it does at the surface. It does not snap or shatter. Instead, it adjusts. The mineral grains within it shift position incrementally, sliding past one another along boundaries too small to see, rearranging themselves into configurations that occupy slightly less space. This is not a fast process. It happens over timescales that make human observation impossible. You cannot watch granite compress. You can only infer it from the structure of rocks brought to the surface by tectonic forces, rocks that once existed deep within the crust, and now bear the evidence of their history written into their crystalline fabric. Geologists call these deformation features, and they are everywhere once you know how to read them. Elongated mineral grains, foliated textures, bands of darker and lighter material aligned in directions that reveal the stress fields that shape them. The deeper you go, the more these features appear, until at a certain depth the rocks themselves begin to transition into forms that no longer resemble anything familiar from the surface. The boundary between crust and mantle is not a sharp line. It is a transition zone, a region where the composition and behavior of rock change gradually as pressure increases. The crust, light and brittle near the surface, gives way to the mantle, which is denser, hotter, and under such immense pressure that its mineral structures can no longer remain stable in the forms they held closer to the surface. This boundary is called the Mohorovicic discontinuity, named after the Croatian seismologist who first detected it by observing how seismic waves change velocity as they pass from crust into mantle. The waves do not stop. They do not reflect back entirely. They simply speed up because the material they are traveling through has become denser and more rigid, compressed into a state where sound moves faster through it than it does through the rock above. The Moho, as it is often called, lies roughly 30 to 50 kilometers beneath continents, shallower beneath oceans where the crust is thinner. It is not a place you can visit. It is not a surface you can touch. It is simply a depth at which the cumulative pressure has reached a point where one type of material becomes another, where the minerals that make up crustal rock are no longer thermodynamically stable and are replaced by minerals that can exist only under greater confinement. Olivine is the dominant mineral of the upper mantle, a dense silicate that forms at high temperatures and pressures in conditions where granite could not persist. It is green when pure, though impurities often darken it, and it crystallizes in structures that pack atoms more tightly than the minerals of the crust. Olivine is what basalt becomes when pressure and heat strip away the lighter elements, when the material is forced into configurations that minimize volume and maximize density. It is stable across a broad range of depths, from the Moho down to roughly 400 kilometers, and throughout this region the pressure continues to rise in direct proportion to the weight of everything above. At 100 kilometers depth, the pressure exceeds 30,000 atmospheres. At 200 kilometers it doubles again. The rock at these depths is not molten despite the heat, because pressure raises the melting point of minerals far beyond what temperature alone can achieve. The mantle flows, but it flows as a solid deforming over millions of years in response to thermal currents and gravitational forces, moving at rates measured in centimeters per year, carrying continents on its surface like debris floating on a slow river. This is convection, but not the convection of boiling water or rising air. It is the convection of solid rock moving through solid rock, driven by temperature differences too subtle to feel and pressure gradients too vast to comprehend. Heat generated by radioactive decay deep within the Earth rises slowly through the mantle, warming the material just enough to make it slightly less dense than the rock around it, and that small difference in density is sufficient over geologic time to cause motion. The heated rock rises, the cooler rock sinks, and the entire mantle circulates in patterns that take hundreds of millions of years to complete one full cycle. This motion is what drives plate tectonics, what opens ocean basins and closes them again, what builds mountains and wears them down. But it is invisible from the surface, perceptible only through its effects, through the motion of continents measured by GPS satellites, through the earthquakes that mark the boundaries where one plate grinds past another. The mantle moves because pressure allows it to move, because the atoms within olivine and its companion minerals are packed tightly enough that they can slide past one another without breaking the bonds that hold the crystal structure together. This is not fragility. It is a kind of strength that only exists under confinement, a plasticity born from the inability to expand. At 400 kilometers beneath the surface, something fundamental changes. The pressure at this depth approaches 130,000 atmospheres, and olivine, which has been the stable form of mantle rock since the Moho, can no longer maintain its crystal structure. The atoms within it are being pressed inward with such force that they must rearrange themselves into a tighter configuration, one that occupies less space for the same mass. This is not a chemical reaction. The composition remains identical, the same atoms in the same proportions, but the geometry shifts. Olivine transforms into a mineral called wadsleyite, which has the same chemical formula, but a different internal architecture, one where oxygen atoms are packed more closely around silicon and magnesium, where the empty spaces between atoms shrink to accommodate the increasing load from above. This transformation releases a small amount of energy, enough that seismologists can detect it as a subtle change in seismic wave velocity, a boundary they call the 410-kilometer discontinuity. It is not dramatic. It does not mark a sudden shift in behavior or appearance. It is simply the depth at which pressure makes one arrangement of atoms less favorable than another, where thermodynamics quietly selects a new equilibrium. Wadsleyite persists for another 120 kilometers, stable across a narrow window of depth, where pressure continues to climb, but has not yet reached the point where even this denser form must yield. The mantle in this region is still flowing, still convecting, still solid despite temperatures that would melt the same material if it were brought to the surface and released from confinement. Pressure and temperature work together here, not in opposition. The heat makes atoms vibrate more energetically, increasing their tendency to move and flow. The pressure holds them together, preventing that movement from becoming chaotic, forcing it to occur within the constraints of a crystalline lattice that remains intact even as it deforms. The result is a kind of motion that has no analog in everyday experience, rock flowing like honey, but only over timescales measured in millions of years, only across distances measured in hundreds of kilometers. If you could somehow stand within the mantle at this depth and live long enough to observe it, you would see nothing. The motion is too slow. The deformation is incremental beyond perception. Yet over the lifespan of a continent, this flow is what drives everything, what recycles oceanic crust back into the deep interior, what supplies volcanoes with fresh material, what erases the oldest surfaces of Earth and replaces them with new ones. At 520 kilometers, wadsleyite gives way to ringwoodite, another polymorph of the same chemical composition, another rearrangement of atoms into an even tighter structure. This transformation marks the 520-kilometer discontinuity, another seismic boundary detected only because waves traveling through the Earth suddenly speed up again as they pass through material that is denser still. Ringwoodite can hold more water in its crystal structure than either olivine or wadsleyite, not as liquid water, but as hydroxyl groups bonded into the mineral lattice, trapped there by pressure that prevents their release. This water, though it is not water in any form you could drink or recognize, may represent a reservoir larger than all the oceans on Earth's surface combined, locked within the mantle in a form that will never be accessible, never emerge, never evaporate. It is water only in the sense that hydrogen and oxygen are present, bound so tightly that they cannot move independently, cannot form the molecules we associate with wetness or flow. The presence of this hydrogen slightly weakens the mantle, makes it marginally easier for the rock to deform, and this has implications for how convection currents move through the transition zone, how material circulates between the upper and lower mantle, how the planet as a whole regulates its internal heat over billions of years. The transition zone, as geologists call this region between 400 and 660 kilometers depth, is where pressure begins to dominate over all other factors in determining what form matter can take. Temperature still matters. The mantle is hot here, nearly 2,000 degrees Celsius, but it is pressure that dictates which minerals can exist, which crystal structures are stable, which atomic arrangements occupy the least volume. Below 660 kilometers, ringwoodite itself becomes unstable, and the mantle undergoes its most significant transformation, the one that separates the upper mantle from the lower mantle. At this depth, pressure exceeds 230,000 atmospheres, and the silicate minerals that have dominated the mantle up to this point break apart and recombine into entirely new forms. Ringwoodite dissociates into two separate minerals, bridgmanite and ferropericlase, both of which are denser than anything that exists naturally at lower pressures, both of which have crystal structures designed, in a sense, by the sheer weight of the planet pressing down on them. Bridgmanite is the most abundant mineral on Earth by volume, though humans have never found it at the surface except in meteorites, where impact shocks briefly recreated the pressures of the lower mantle. It is the rock that makes up most of the planet's mass, the material that fills the vast shell between the transition zone and the core, and it exists only because pressure will not allow it to be anything else. This is the lower mantle, and it extends downward for nearly another 2,000 kilometers, a region so vast that it contains more than half of Earth's total mass, a shell of rock compressed into forms that bear no resemblance to anything exposed by erosion or brought up by volcanic eruptions. The pressures here are beyond the reach of laboratory experiments conducted under normal conditions, beyond what diamond anvil cells can sustain for more than brief moments, beyond what we can fully simulate except through computer models that approximate how atoms behave when packed together with forces measured in millions of pounds per square inch. The lower mantle is a realm of stillness that moves. It flows but so slowly that the motion becomes almost theoretical. A displacement of material measured in millimeters per year, convection cells that take hundreds of millions of years to complete a single circulation. The pressures here suppress nearly all the mechanisms that allow rapid deformation. There are no fractures, no faults, no sudden slippages of one mass against another. The rock cannot break because breaking requires the creation of new surfaces, the separation of material along planes of weakness, and pressure eliminates all weakness by forcing everything into its most compact possible state. Instead, the lower mantle deforms through diffusion creep, individual atoms migrating slowly through the crystal lattice, moving from regions of high stress to regions of lower stress, accumulating gradually until the entire structure has shifted position without any single grain moving perceptibly. This is motion at the atomic scale, aggregated across volumes measured in cubic kilometers, sustained across timescales that make mountain building look sudden. Bridgmanite, which constitutes roughly 3/4 of the lower mantle's composition, has a perovskite structure, a lattice arrangement where silicon atoms are surrounded by 6 oxygen atoms in a tight octahedral cage, and magnesium and iron atoms fill the spaces between these cages. This geometry is extraordinarily efficient in terms of packing density. It leaves almost no empty space, no room for the atoms to rattle or shift freely. Under the pressures of the lower mantle, which range from 230,000 atmospheres at the top to over 1 million atmospheres near the core mantle boundary, Bridgmanite's structure remains stable because there is simply no other arrangement that occupies less volume. The atoms are locked into position not by strong chemical bonds alone, but by the weight of everything above, pressing them into a configuration from which they cannot escape. Temperature tries to disrupt this order. At depths of 1,500 kilometers, temperatures exceed 2,500 degrees Celsius, but pressure overwhelms thermal motion, keeping the crystal structure intact even as the atoms vibrate with increasing energy. Ferropericlase, the second major mineral of the lower mantle, is simpler in structure but equally constrained. It consists of magnesium oxide and iron oxide in a cubic lattice, each metal atom surrounded by 6 oxygen atoms in a regular geometric pattern. Iron in ferropericlase exists primarily in the ferrous state at the top of the lower mantle, but as pressure increases with depth, some of it undergoes a spin transition, a change in the electronic configuration of the iron atoms that makes them occupy slightly less space. This transition happens gradually across a broad depth range, not at a single boundary, and it affects how heat moves through the lower mantle, how the material absorbs and releases seismic energy, how it responds to the slow gravitational stirring that drives convection. The spin transition is subtle, invisible, detectable only through careful analysis of seismic wave velocities and laboratory experiments that attempt to recreate lower mantle conditions using lasers and diamond anvils to compress tiny samples of synthetic ferropericlase. These experiments can sustain pressures of 1 million atmospheres for only fractions of a second, just long enough to measure how the material's properties change, just long enough to confirm that the models predicting these transitions are at least approximately correct. What we know about the lower mantle comes almost entirely from indirect observation. No sample of Bridgmanite from the deep earth has ever been recovered intact. The mineral is stable only under high pressure, and when pressure is released, when a rock containing it is brought to the surface by tectonic forces or volcanic eruptions, Bridgmanite decomposes immediately into lower density minerals that can exist at atmospheric pressure. The only natural Bridgmanite ever found on Earth's surface came from meteorites, fragments of other planets or asteroids that experienced brief moments of extreme shock during collisions in space, impacts violent enough to generate pressures comparable to the lower mantle, for just long enough to form Bridgmanite crystals that were then preserved as the material cooled rapidly in the vacuum of space. These crystals are tiny, often only micrometers across, but they confirm that the mineral we think dominates Earth's interior does in fact exist, that our calculations and models are describing something real rather than purely theoretical. Beyond these meteoritic samples, everything we know about the lower mantle comes from seismology, from the speed at which earthquake waves travel through it, from the way those waves bend and reflect at boundaries, from the subtle variations in velocity that reveal differences in temperature or composition or mineral phase. Seismic waves are remarkable in their ability to carry information across planetary distances. An earthquake in Japan sends waves through the entire Earth, waves that arrive at seismometers in South America minutes later, having traveled through regions no human will ever visit, through material no drill will ever sample. These waves tell us that the lower mantle is not uniform. They reveal large structures called superplumes, rising columns of hotter material originating near the core mantle boundary, buoyant regions where temperatures are perhaps 100 or 200 degrees warmer than the surrounding mantle, enough to make the rock fractionally less dense and therefore capable of rising through convection. The superplumes rise slowly, perhaps a few centimeters per year, and they persist for tens or hundreds of millions of years, feeding volcanic hotspots at the surface like Hawaii or Iceland, with fresh material from depths of nearly 3,000 kilometers. Seismic waves also reveal subducted slabs, remnants of oceanic crust that sank at subduction zones and descended through the mantle, cooling as they fell, eventually piling up near the core mantle boundary, where they form dense accumulations of old, cold rock that may sit there for billions of years before being reheated and reintegrated into the convection cycle. The deeper you descend through the lower mantle, the more the pressure begins to dominate every other physical property. At 1,000 kilometers depth, the pressure exceeds 400,000 atmospheres. At 2,000 kilometers, it approaches 800,000 atmospheres. The temperature rises too, increasing roughly by 1 degree Celsius for every kilometer of descent. But this thermal gradient is gentle compared to the relentless accumulation of gravitational force. By the time you reach the base of the lower mantle, nearly 2,900 kilometers beneath the surface, the pressure has climbed to 1,300,000 atmospheres and the temperature hovers near 4,000 degrees Celsius. These are conditions that exist nowhere else in the solar system except in the interiors of other large rocky planets. Conditions so extreme that the material here behaves in ways that can only be approximated in laboratories using equipment that pushes the boundaries of what physics and engineering can achieve. At this depth, even bridgemanite begins to falter. The perovskite structure that has been stable throughout most of the lower mantle starts to show signs of instability when pressure exceeds 1,200,000 atmospheres. The atoms within the crystal lattice are compressed so tightly that the bonds between them can no longer maintain the same geometric arrangement. The result is a phase transition to a mineral called post-perovskite, a form of bridgemanite, with a slightly different internal structure, one where the silicon-oxygen octahedra are no longer isolated from one another, but instead linked into layers, stacked like sheets of paper compressed under immense weight. This transition occurs across a thin boundary zone called the D-double-prime layer, a region perhaps 200 kilometers thick that sits directly above the outer core. The D-double-prime layer is one of the most enigmatic regions of Earth's interior, a place where seismic waves behave strangely, where velocities change in unexpected ways, where the properties of the mantle are influenced not only by pressure from above, but also by heat radiating upward from the core below. Post-perovskite is denser than bridgemanite, as all phase transitions at increasing depth must be, but only marginally so, a difference of perhaps 2% in volume. This small change is enough, however, to affect how seismic waves propagate through the region, creating sharp reflections that geophysicists can detect with sensitive instruments. The discovery of post-perovskite came not from finding a sample, none exists and none can exist outside the deep mantle, but from high-pressure experiments conducted in the early 2000s, experiments that compressed tiny crystals of bridgemanite between diamond anvils while simultaneously heating them with lasers, attempting to recreate the conditions of the lowermost mantle in a laboratory chamber smaller than a grain of sand. When researchers finally achieved the necessary pressure and temperature, they observed a sudden change in the material's X-ray diffraction pattern, a signature indicating that the crystal structure had shifted into a new configuration. This was post-perovskite, predicted theoretically decades earlier, but confirmed only when technology advanced enough to reach pressures that had previously been inaccessible. The D-double-prime layer is also where the mantle's convection becomes more complex. Heat from the core warms the base of the mantle, creating thermal instabilities that lead to the formation of plumes, rising columns of buoyant material that carry heat upward toward the surface. These plumes do not rise quickly. They drift upward at rates measured in centimeters per year, taking tens of millions of years to traverse the entire thickness of the mantle. Some of them reach the surface and manifest as volcanic hotspots, but many do not, stalling partway through their ascent or dissipating as they lose thermal energy to the surrounding rock. The D-double-prime layer is also where subducted slabs accumulate after their long descent from the surface. These slabs, composed of old oceanic crust and lithosphere, are colder and denser than the surrounding mantle, and when they reach the core mantle boundary, they spread out horizontally, forming what geophysicists call slab graveyards, regions where ancient seafloor, some of it hundreds of millions of years old, lies compressed and heated at the base of the mantle, waiting to be reabsorbed into the convection cycle. The existence of these graveyards was inferred from seismic tomography, a technique that uses thousands of earthquake recordings to create three-dimensional maps of seismic wave velocity variations throughout the Earth. The cold slabs show up as regions where waves travel faster than average, because colder rock is denser and more rigid, and these fast anomalies cluster near the core mantle boundary in specific locations beneath the Pacific Ocean and other regions where subduction has been active for long periods of geologic time. The core mantle boundary itself is not a smooth, uniform surface. It is irregular, shaped by the interaction between the solid rock of the mantle and the liquid iron of the outer core below. The core is hotter than the mantle. Temperatures at the boundary may exceed 4,500 degrees Celsius, and this temperature contrast drives heat flow upward, maintaining the thermal engine that powers mantle convection and, indirectly, plate tectonics. The boundary is also where the character of matter changes abruptly. Above it, you have silicate rock, minerals composed of silicon, oxygen, magnesium, and iron, all compressed into the densest forms that silicates can take. Below it, you have molten metal, primarily iron with smaller amounts of nickel, and lighter elements like sulfur or oxygen dissolved into the liquid. The density contrast across this boundary is dramatic. The outer core is nearly twice as dense as the lowermost mantle. And this sharp change in material properties makes the core mantle boundary one of the most seismically reflective surfaces inside the Earth. Seismic waves bounce off it, refract through it, convert from one type to another as they cross it, and these behaviors allow geophysicists to map its shape and detect features that suggest dynamic interaction between core and mantle, regions where hot core material may be eroding the base of the mantle, or where cold mantle material may be protruding downward into the core. The outer core begins where rock ends, 2,900 kilometers beneath your feet, at a boundary so fundamental that it marks the transition from solid to liquid, from silicate to metal, from a material that transmits all types of seismic waves to one that allows only compression waves to pass through. This boundary is sharp, geologically speaking, perhaps only a few kilometers thick, and crossing it means entering a realm where the dominant substance is iron, heated to temperatures that would vaporize it instantly at the surface, but kept liquid here by pressures so immense that the metal cannot expand into gas, cannot escape the gravitational prison that confines it. The outer core is a shell of molten iron, roughly 2,200 kilometers thick, containing about 30% of Earth's mass, and it exists in a state that has no terrestrial analog. We have never touched liquid iron at these pressures. We have never contained it, never observed it directly, never measured its properties except through inference and approximation. Iron at the surface melts at 1,538 degrees Celsius under normal atmospheric pressure. But pressure raises the melting point of most materials, and iron is no exception. At the pressures of the core mantle boundary, 1,300,000 atmospheres, iron's melting point climbs to nearly 5,000 degrees Celsius. The core is at least that hot, perhaps hotter, and so the iron remains liquid despite the enormous pressure trying to force it into a solid state. This liquid is not like water. It is dense, roughly 7 times denser than rock, nearly 14 times denser than water, and it is viscous, though not as viscous as rock in the mantle. It flows more readily than the solid mantle above it, but it does not flow freely. It moves sluggishly, churning in convection currents driven by heat released from the inner core and by the gradual cooling of the Earth over billions of years. This motion is what generates Earth's magnetic field, a process called the geodynamo, where the movement of electrically conductive liquid iron creates electric currents, and those currents in turn generate magnetic fields that extend outward through the mantle, through the crust and into space, forming the magnetosphere that shields the surface from solar wind and cosmic radiation. We know the outer core is liquid because seismic waves tell us so. When an earthquake occurs, it generates 2 main types of body waves: primary waves, which are compression waves that can travel through any material, and secondary waves, which are shear waves that can only travel through solids. Primary waves pass through the entire Earth, bending and slowing as they enter the core but continuing onward until they emerge on the far side of the planet. Secondary waves, however, disappear when they reach the core mantle boundary. They do not penetrate the outer core at all, because liquids cannot support shear stress. They flow when pushed sideways rather than transmitting the motion as a wave. This absence of secondary waves in the core's shadow zone was one of the first pieces of evidence that led early seismologists to conclude that the outer core must be liquid, a conclusion reached in the early 20th century and confirmed repeatedly by every subsequent observation. The core is opaque to shear waves, and this opacity defines its liquid nature more clearly than any other measurement. The convection within the outer core is not uniform. It is turbulent, chaotic, driven by thermal and compositional buoyancy as lighter elements dissolved in the iron rise toward the core mantle boundary, while denser, hotter iron sinks toward the inner core. The exact composition of the outer core remains uncertain. Iron is the dominant element, constituting roughly 85% of the mass, with nickel making up another 10%. But the remaining 5% consists of lighter elements whose identity is still debated. Sulfur, oxygen, silicon, and hydrogen have all been proposed as candidates, elements that dissolve into liquid iron under core conditions and reduce its density just enough to match the values inferred from seismic observations. These light elements are important because they affect how the outer core convects, how heat moves through it, how the magnetic field is generated and sustained. Their presence makes the outer core slightly less dense than pure iron would be at the same pressure and temperature, and this density difference drives some of the convection by creating buoyancy forces that stir the liquid metal. The pressure within the outer core increases steadily with depth, from 1,300,000 atmospheres at the top to over 3 million atmospheres at the base, where the outer core meets the inner core. This gradient is less steep than the pressure gradient in the mantle because the core is liquid, and liquids are more compressible than solids. They can reduce their volume more significantly in response to increasing pressure. But even so, the pressure at the base of the outer core is staggering, enough to compress iron to densities that exceed 12 grams per cubic centimeter, enough to alter the electronic structure of iron atoms in ways that affect how they conduct electricity and heat. The liquid iron at these depths is not the same substance in any meaningful sense as the iron we encounter at the surface. Its atoms are squeezed into configurations where the usual rules of chemistry no longer fully apply, where quantum mechanical effects become significant, where the distinction between liquid and solid begins to blur in ways that challenge our understanding of matter itself. At 5,100 kilometers beneath the surface, something changes again. The pressure here exceeds 3,300,000 atmospheres, and at this threshold, iron can no longer remain liquid. It is not that the temperature drops. The inner core is actually hotter than the outer core, with temperatures estimated at 5,200 to 5,700 degrees Celsius, perhaps even higher. But pressure at this depth finally overwhelms thermal motion and forces the iron atoms into a crystalline lattice, locking them into place despite the intense heat trying to keep them free. This is the inner core, a solid sphere of iron and nickel roughly 1,200 kilometers in radius, suspended within the liquid outer core, slowly rotating at a rate that may differ slightly from the rotation of the mantle and crust above it. The inner core grows incrementally over geologic time, as the Earth cools and more liquid iron from the outer core freezes onto its surface, a process that releases latent heat and lighter elements that then rise into the outer core, driving some of the convection that sustains the magnetic field. The transition from liquid outer core to solid inner core is not abrupt in the way that the core mantle boundary is. It occurs across a thin, mushy layer where iron crystals form and float within the remaining liquid, where the material is neither fully solid nor fully liquid, but something in between, a slurry of crystallizing metal that settles gradually onto the surface of the inner core. This boundary is detectable seismologically, because seismic waves behave differently when they pass through it. Compression waves slow down slightly, and shear waves, which could not exist in the liquid outer core, reappear in the solid inner core, though they are weak and difficult to detect because the inner core is small relative to the rest of the planet, and because the waves that reach it have already traveled through thousands of kilometers of mantle and core, losing energy with every interaction and boundary crossing. The existence of the inner core was not confirmed until 1936, when Danish seismologist Inge Lehmann analyzed seismic data from earthquakes, and noticed that compression waves were arriving at certain locations slightly earlier than expected, as if they had taken a shortcut through a denser, faster medium deep within the core. Her insight revealed the inner core's presence, a discovery made not by drilling or sampling, but by listening carefully to the way the Earth rings when struck by seismic energy. The inner core is the most compressed matter in the Earth. The pressure at its outer boundary is over 3 million atmospheres, and at the very center it may exceed 3,600,000 atmospheres. Under these conditions, iron atoms are packed so tightly that the distance between them is only slightly larger than the diameter of the atoms themselves. The crystal structure is thought to be hexagonal close-packed, one of the most efficient ways to arrange spheres in three-dimensional space, though some evidence suggests that the structure may be more complex, with different crystal orientations in different regions, possibly aligned by the forces generated as the inner core rotates within the magnetic field of the outer core. The iron here is not pure. It contains nickel, perhaps 5 to 10% by mass, and possibly small amounts of lighter elements trapped during the freezing process, elements that cannot easily be incorporated into the crystal lattice, but remain as impurities at grain boundaries or within defects in the crystalline structure. The inner core is also anisotropic, meaning that seismic waves travel through it at different speeds depending on their direction. Waves traveling parallel to Earth's rotation axis move faster than waves traveling perpendicular to it, a difference of a few percent that suggests the iron crystals within the inner core are aligned preferentially in one direction, possibly by convection currents in the overlying outer core, or by magnetic forces acting on the solidifying iron over millions of years. This anisotropy was unexpected when it was first discovered in the 1980s, and it remains only partially explained. Some models suggest that the inner core may itself be convecting, not as a liquid, but as a solid that deforms over geologic timescales, with crystals slowly migrating from the equator toward the poles and then sinking back toward the center in a circulation pattern driven by the release of latent heat during solidification. Other models propose that the anisotropy is frozen in, a relic of the conditions under which the inner core first formed billions of years ago, preserved because the material is now too stiff to rearrange itself even over planetary timescales. The density of the inner core is extraordinary, roughly 13 grams per cubic centimeter, nearly 7 times denser than surface rock, twice as dense as lead. This density is not due to composition alone, but to the relentless compression of pressure acting on every atom, squeezing them into the smallest possible volume, eliminating nearly all the empty space that exists in materials at lower pressures. If you could somehow extract a cubic centimeter of inner core material and bring it to the surface, releasing the pressure, it would expand violently, its density dropping by perhaps 20 or 30% as the atoms rearrange themselves into a looser configuration appropriate for atmospheric pressure. The material would also cool rapidly, solidifying into a form of iron that bears little resemblance to the high-pressure phase that existed at the core, and any light elements dissolved in it would likely escape as gases or react with the atmosphere, leaving behind a sample that told you almost nothing about what the inner core is actually like in situ. At the very center of the Earth, 6,371 kilometers beneath the surface, there is a point where the pressure reaches its maximum and then has nowhere else to go. This is not a dramatic threshold. There is no sudden change in material or phase, no boundary that seismic waves can detect. It is simply the geometric center of a sphere, the place where every direction is outward, where the weight of the entire planet presses inward from all sides with equal force, creating a pressure estimated at 3,600,000 atmospheres, perhaps slightly more. At this point, the compression is as extreme as planetary gravity alone can make it. Any further increase would require additional mass, a larger planet, a stronger gravitational field. The center is not a void or a cavity. It is solid iron compressed to its absolute limit, atoms held in place by forces that allow no further reduction in volume. There is nothing special about the center, except that it is where the accumulation of weight finally converges, where the arithmetic of depth reaches its conclusion. The temperature at the center is uncertain, but likely exceeds 5,000 degrees Celsius, possibly approaching 6,000. This is as hot as the surface of the Sun, though the comparison is misleading because the conditions are so fundamentally different. The Sun's surface is plasma in the vacuum of space, matter ionized and radiating energy outward with no confining pressure to hold it together. Earth's center is solid metal locked under pressure so immense that it cannot melt, cannot expand, cannot do anything but remain exactly where it is, vibrating with thermal energy that has no outlet, no way to escape except by slowly diffusing outward through the surrounding material over geologic time. The heat at the center is primordial, left over from the planet's formation, when countless collisions between planetesimals released kinetic energy as heat, supplemented by the decay of radioactive isotopes that have been generating warmth steadily for over 4.5 billion years. This heat moves outward incrementally, traveling through the inner core by conduction, through the outer core by convection, through the mantle by a combination of both, taking millions of years to migrate from the center to the surface where it is finally radiated into space as infrared energy. The pressure at the center is not exerted by any single thing. It is the cumulative weight of every layer above, every kilometer of rock and metal, every gram of mass in the mantle and crust and oceans and atmosphere, all of it pulled downward by gravity, all of it pressing inward toward this point. If you could somehow remove a spherical shell of material from the outer core, reducing the planet's mass, the pressure at the center would drop immediately, not because anything at the center changed, but because there would be less weight bearing down from above. Pressure at depth is not an intrinsic property of the material. It is a consequence of position within a gravitational field, a result of how much mass lies between you and empty space. The iron at the center is identical in composition to the iron just beneath the core mantle boundary, but it is compressed more because it supports more weight, because it is deeper, because there is more planet above it than there is above anywhere else. This pressure has been building since the Earth first formed, since gravity pulled the scattered debris of the early solar system into a cohesive mass. In the beginning, the planet was likely a molten or semi-molten body, heated by the energy of accretion and the decay of short-lived radioactive isotopes. Over time, it cooled, and as it cooled, the iron separated from the silicates and sank toward the center in a process called differentiation, driven by the fact that liquid iron is denser than molten rock and therefore falls when the two are not solid. This sinking created the core, and the energy released as iron descended and converted gravitational potential energy into heat may have been enough to remelt parts of the planet, creating a magma ocean that persisted for millions of years before finally solidifying into the layered structure we see today. The pressure at the center increased as the planet grew, as more mass was added, as gravity strengthened and pulled everything inward more forcefully. It reached something close to its current value once the planet achieved its final mass, and it has remained roughly constant since then, fluctuating only slightly as the Earth's radius changes. The planet is very slowly shrinking as it cools, and this contraction slightly increases the pressure at the center, though the effect is negligible over human timescales. The center of the Earth is inaccessible in a way that is more absolute than the inaccessibility of distant stars or the far side of the universe. Those places are far away, separated from us by distance and time, but in principle we could travel to them if we had sufficient energy and patience. The center of the Earth is separated from us not by distance alone, but by the material of the planet itself, by thousands of kilometers of rock and metal that cannot be bypassed or tunneled through with any conceivable technology. The pressures and temperatures increase continuously with depth, and there is no path through them that does not require surviving conditions that would destroy any material we know how to make. Even if we could drill through the crust and mantle, even if we could penetrate the outer core without the borehole collapsing or the drill bit melting, we would still face the inner core, solid iron so compressed that it would deform any probe instantly, reducing it to a smear of atoms distributed across the crystalline lattice. What we know about pressure at these depths comes from measurement and inference, from laboratory experiments that attempt to recreate conditions that exist only in planetary interiors, from mathematical models that describe how matter behaves when compressed beyond the reach of direct observation. Diamond anvil cells, devices that use the hardest natural material to compress microscopic samples, between two precisely cut diamonds, can reach pressures of several million atmospheres, enough to simulate conditions in the lower mantle or outer core, but only for tiny volumes and brief durations. The samples are often smaller than the width of a human hair, and the high-pressure phase exists only as long as the force is maintained. Release the pressure, and the sample reverts to its low-pressure form, often explosively, as the atoms rearrange themselves back into the configurations stable at atmospheric pressure. These experiments are difficult, expensive, and limited in scope, but they provide the only direct measurements we have of how materials behave under extreme compression, and they serve as calibration points for theoretical models that attempt to extrapolate from laboratory conditions to planetary conditions. Seismology offers a different kind of knowledge, one based not on samples but on waves, vibrations that travel through the Earth at speeds determined by the density and elastic properties of the materials they pass through. Every earthquake generates seismic waves that propagate in all directions, and by recording these waves at hundreds of seismometers distributed across the globe, geophysicists can reconstruct the internal structure of the planet with remarkable precision. The technique is called seismic tomography, and it works much like a medical CT scan, building a three-dimensional image from thousands of one-dimensional measurements. The waves tell us where boundaries are, where density changes, where temperature varies, where the material is more or less rigid. They tell us that the mantle is mostly solid but flows slowly, that the outer core is liquid and convects rapidly, that the inner core is solid and anisotropic. But they do not tell us directly what the pressure is at any given depth. Pressure must be inferred from the density, and density is inferred from the wave velocities, and the velocities are measured with instruments that sit on the surface, thousands of kilometers away from the regions they are probing. The chain of inference is long, and each step introduces uncertainty. Though the uncertainties are smaller than you might expect, seismology is mature enough that the basic structure of the Earth is known with confidence, even if the details remain contested. Theoretical models provide a third source of knowledge, one based on fundamental physics rather than observation. The equations of state that describe how pressure, temperature, and density are related come from quantum mechanics, from thermodynamics, from statistical mechanics, from principles that apply equally to atoms in a laboratory and atoms at the center of the Earth. These equations can be solved numerically using computers, and the results can be compared to seismic observations and laboratory experiments to check whether the models are accurate. When all three sources agree, when the laboratory data, the seismic measurements, and the theoretical predictions converge on the same values, we can be reasonably confident that we understand what is happening, even if we cannot visit the place we are describing. This is how science works at the limits of accessibility. By cross-checking multiple independent lines of evidence, by building models that explain all the data, by testing those models against new observations and refining them when discrepancies appear. But there is a kind of uncertainty that cannot be eliminated, a fundamental limit on what we can know about regions we will never visit. We do not know, for instance, whether there are small-scale structures in the core that are too subtle for seismic waves to detect, whether there are chemical heterogeneities or convection patterns that exist below the resolution of our instruments. We do not know whether the inner core is growing uniformly or whether it is crystallizing faster on one side than the other, creating asymmetries that might affect the magnetic field or the rotation rate. We do not know whether the core mantle boundary is smooth or rough at small scales, whether it is chemically sharp or gradational, whether reactions between mantle rock and core metal are occurring, and if so, what products they are producing. These questions are not merely academic. They affect how we understand the planet's evolution, how we interpret magnetic field variations, how we predict long-term changes in climate or sea level driven by the slow cooling of the interior. But they are difficult to answer because the signals we receive from depth are averaged over large volumes, smeared out by the passage of seismic waves through thousands of kilometers of heterogeneous material, filtered by the limits of our instruments and the spacing of our seismometer networks. And so we live with uncertainty, not the uncertainty of ignorance, but the uncertainty of incomplete information, the knowledge that we understand the broad outlines, but not every detail, that we have mapped the major features, but not the fine structure. This is the condition of studying anything truly remote, anything separated from us by barriers we cannot cross. The pressures at the center of the Earth have existed for more than 4 billion years. They were established when the planet first differentiated, when iron separated from silicate and sank inward, and they have remained essentially constant ever since. The core does not experience weather, does not undergo seasonal changes, does not respond to anything happening at the surface in any measurable way. The continents drift, oceans open and close, ice ages come and go, entire mountain ranges rise and erode away, and through all of this the pressure at the center remains unchanged, varying by fractions of a percent at most as the planet slowly cools and contracts. This is a kind of permanence that has no analog in surface environments, where everything is transient, where erosion and deposition reshape landscapes on timescales of thousands or millions of years, where even the hardest rocks eventually crumble under the influence of water and temperature change and biological activity. The deep interior is immune to these processes. It exists in a state of equilibrium that has persisted since the Hadean Eon, since the time when Earth's surface was still molten or semi-molten and the first stable crust was only beginning to form. Pressure at these depths is not destructive in the way we usually think of compression. It does not crush or shatter or break, it stabilizes. The materials under extreme pressure are locked into configurations that cannot change because there is no path to a lower energy state, no way to rearrange atoms into a form that occupies less space or releases energy by transforming. The inner core is solid, not because it is cold, but because pressure forces it to be solid, and it will remain solid as long as the pressure is maintained, which is to say, as long as the Earth exists. The same is true of bridgemanite in the lower mantle, of ringwoodite in the transition zone, of all the high-pressure phases that exist only because gravity will not permit them to be anything else. These materials are stable in the same way that a balanced rock on a flat surface is stable, not because they are in their lowest possible energy state, but because there is no available mechanism for them to reach a lower state. Remove the pressure, and they would transform instantly, but the pressure is not going anywhere. It is a consequence of mass and gravity, and those are properties that cannot be switched off or reduced without fundamentally altering the planet itself. This stability extends to geological timescales that are difficult to comprehend. The inner core grows by perhaps 1 millimeter per year as the Earth cools and more iron crystallizes from the outer core. At this rate, it would take 1 billion years for the radius to increase by a single kilometer. The convection currents in the mantle move at centimeters per year, fast by geological standards, but imperceptibly slow by human ones. A plume rising from the core mantle boundary to the surface takes 50 million years to complete its journey, and the rock it carries arrives at the surface transformed by the slow decrease in pressure it experiences along the way, minerals converting from high-pressure phases to low-pressure phases as the load above them diminishes. These transformations happen continuously, invisibly, everywhere in the deep Earth, driven by the same pressure gradients that have existed since the planet formed. The deep interior is not static, but its motion is so slow and its structure so stable that from any human perspective it might as well be eternal. Pressure also preserves. The rocks of the lower mantle contain chemical signatures from the early solar system, isotopic ratios and trace element abundances that have survived for 4.5 billion years because the material has never been brought to the surface, never been exposed to water or oxygen or any of the reactive conditions that would alter its composition. The core, similarly, is a reservoir of primordial material, iron and nickel and light elements that have been isolated from the surface environment since differentiation occurred, maintaining a record of the planet's original composition in a form that will never be accessible, but can be inferred from models and from the composition of meteorites, which formed from the same material as Earth and underwent similar differentiation processes in their own planetary bodies. These deep reservoirs are archives, holding information about the conditions under which the solar system formed, about the chemistry of the nebula from which the planets condensed, about the early history of Earth before life appeared, or oceans formed, or the atmosphere became oxygenated. They are archives written in a language we can barely read, preserved in a place we cannot visit, maintained by pressure that allows no corruption or decay. There is something profoundly indifferent about the deep Earth. It operates according to principles that have nothing to do with biology, with climate, with the thin film of water and air that makes the surface habitable. The pressure at 6,000 kilometers depth does not care whether life exists above it. It does not respond to mass extinctions or ice ages or the rise and fall of civilizations. It simply is, a consequence of geometry and gravity, present whether anyone notices it or not. This indifference is not hostile, it is merely complete. The deep interior has no awareness of the surface, no mechanism by which surface processes could influence it in any significant way. The weight of the oceans adds a negligible fraction to the pressure in the mantle. The erosion of mountains, which removes billions of tons of rock and redistributes it elsewhere, barely registers at depths beyond a few hundred kilometers. The entire human enterprise, cities, roads, mines, agriculture, everything we have built or altered, represents a surface perturbation so minor that it would be undetectable even if we had instruments capable of measuring pressure variations at the core mantle boundary, and yet the surface depends entirely on what happens below. The tectonic plates that drift across the globe are carried by mantle convection, driven by heat rising from the core and by the slow descent of cold, dense lithosphere at subduction zones. Volcanic eruptions that build island chains and reshape coastlines are fed by magma generated when mantle rock partially melts as it rises toward the surface, its melting point dropping as pressure decreases, even though temperature remains high. The magnetic field that shields the surface from solar wind and cosmic radiation is generated by the motion of liquid iron in the outer core, a motion sustained by the cooling and crystallization of the inner core, and by compositional convection driven by the separation of light and heavy elements during freezing. Without these deep processes, Earth's surface would be a different place entirely, tectonically dead, volcanically inactive, unprotected from space weather, possibly incapable of sustaining life as we know it. The pressure at depth is part of the infrastructure that makes the surface habitable, even though it operates independently of habitability, even though it existed long before life appeared and will continue long after life, if it ends, has disappeared. We live on a thin shell, a layer of rock just a few tens of kilometers thick, floating on a mantle that extends down for nearly 3,000 kilometers and contains most of the planet's volume and mass. This shell is not stable in any permanent sense. It is constantly being created at mid-ocean ridges and destroyed at subduction zones, recycled through the mantle over timescales of a few 100 million years. The oldest oceanic crust on Earth is less than 200 million years old, young compared to the planet's age, and it is already being pulled back into the mantle, where it will be heated and compressed and eventually remelted or assimilated into the convection cycle. Continental crust is older and more stable, but even continents are not permanent. They drift, collide, break apart, erode. The rocks exposed at the surface today were once buried deep within the crust, subjected to pressures of thousands or tens of thousands of atmospheres before being uplifted by tectonic forces and brought back into the realm where erosion can act on them. The surface is a place of constant exchange, where material moves between the atmosphere, the oceans, the crust, and the mantle in cycles that operate at different rates, but never stop. Pressure mediates these exchanges. It determines which minerals are stable at which depths, which rocks will melt and which will remain solid, which materials will rise and which will sink. It controls the viscosity of the mantle, the rate at which convection occurs, the speed at which tectonic plates move. It shapes the melting behavior of rock, ensuring that magma generated in the mantle is less dense than the surrounding solid material and therefore rises toward the surface, where it erupts as lava or solidifies as intrusive igneous rock. It governs the phase transitions that occur as material descends through the mantle, transforming basalt into eclogite, olivine into wadsleyite, wadsleyite into ringwoodite, ringwoodite into bridgmanite and ferropericlase, each transition occurring at a specific depth determined by the balance between temperature and pressure. These transitions are not arbitrary. They are predictable, repeatable, the same today as they were billions of years ago. the same on Earth as they would be on any other rocky planet of similar size and composition. Understanding pressure is, in a sense, understanding how planets work, not just Earth but any terrestrial world with sufficient mass to generate significant gravitational compression. Mars, smaller than Earth, has lower internal pressures and likely a solid iron core because the pressure at its center is not high enough to raise the melting point of iron above the temperature of the interior. Venus, nearly identical to Earth in size, probably has a similar internal structure, with a liquid outer core and solid inner core, though we cannot confirm this because seismometers have not survived long enough on Venus's hostile surface to record the seismic waves that would tell us for certain. Mercury, the smallest of the terrestrial planets, has a core that makes up an unusually large fraction of its total volume, suggesting an interior pressure distribution different from Earth's, possibly the result of a giant impact early in its history that stripped away much of its mantle and left the dense core intact. Pressure shapes these worlds as much as it shapes Earth, determining which layers exist, which materials are stable at which depths, how heat moves from interior to surface, whether magnetic fields can be sustained. Pressure operates on timescales that are difficult to reconcile with human experience. We are accustomed to processes that unfold over hours or days or years, weather systems that develop and dissipate in a week, rivers that carve valleys over millennia, mountains that rise over millions of years. But the pressure-driven processes of the deep Earth occur so slowly that they become almost invisible, measurable only by their cumulative effects across hundreds of millions or billions of years. The growth of the inner core, for instance, is not something that can be observed directly. It is inferred from models of planetary cooling, from estimates of how much heat the Earth has lost since its formation, from calculations of how fast liquid iron crystallizes at core pressures and temperatures. The result is a growth rate so slow that the inner core's radius has increased by perhaps only a few hundred kilometers since the formation of the first continents, perhaps only a few thousand kilometers since the planet first differentiated. This is growth measured not in human generations, but in the lifetimes of entire ocean basins, in the intervals between supercontinent cycles, in durations that exceed the existence of complex life on Earth. The same is true of mantle convection. The circulation of rock through the mantle takes so long that a single complete cycle, from the moment a piece of lithosphere begins to sink at a subduction zone to the moment it is reheated near the core mantle boundary, rises as part of a plume, reaches the surface and eventually sinks again, can span nearly 1 billion years. This means that some of the material in the deep mantle today may have last been at the surface during the Proterozoic eon, before animals existed, before photosynthesis had oxygenated the atmosphere, when Earth was a fundamentally different planet. That material carries a chemical memory of surface conditions from that time, preserved in isotopic ratios and trace element concentrations that have survived the entire journey through the mantle despite being heated, compressed, and subjected to phase transitions that transform the minerals multiple times. This kind of preservation is possible only because the processes that might erase these signatures, chemical reactions with surrounding rock, diffusion of atoms across grain boundaries, mixing with material of different composition, operate so slowly at mantle conditions that even 1 billion years is not long enough to homogenize everything completely. Pressure, in this sense, is a kind of brake on change. It slows diffusion by increasing the activation energy required for atoms to move from one site to another within a crystal lattice. It inhibits chemical reactions by reducing the mobility of ions and molecules, making it harder for reactants to come into contact and form new bonds. It suppresses melting by raising the temperature at which phase transitions occur, ensuring that rock remains solid even at temperatures that would liquefy it at lower pressures. All of these effects combine to make the deep Earth a place where change happens incrementally, where transformations that would occur rapidly near the surface take millions of years, where the material retains a memory of its history simply because there has not been enough time or enough energy to erase that memory completely. This is not stasis. The mantle is not frozen or unchanging, but it is a kind of slow motion that makes geological time feel almost inadequate, as if even billions of years are barely sufficient for the deep Earth to complete a single cycle of its internal processes. And yet, despite this slowness, the deep Earth is not separate from the surface. The two are connected by flows of mass and energy that move continuously in both directions, though at vastly different rates. Heat flows outward from the core through the mantle to the surface, where it is radiated into space, driving mantle convection and plate tectonics along the way. Material flows downward at subduction zones, carrying water and carbon and other volatiles from the surface into the mantle, and upward at mid-ocean ridges and volcanic hotspots, bringing magma and gases from depth back to the surface. These flows are part of a planetary metabolism, a set of processes that regulate the composition of the atmosphere and oceans, control the availability of nutrients for life, determine the distribution of continents and ocean basins, shape the climate over geological timescales. The pressure at depth is what makes these flows possible, what allows rock to circulate rather than remain static, what prevents the planet from cooling too quickly and becoming tectonically dead like Mars or the Moon. Without pressure to suppress melting in the mantle, without pressure to drive phase transitions that release buoyancy, without pressure to maintain the liquid outer core where the magnetic field is generated, Earth would be a very different world. There is a feedback between surface and deep interior that operates over timescales so long that it is almost invisible, but it is there nonetheless. When continents collide and form supercontinents, they insulate the mantle beneath them, reducing the rate at which heat escapes from the interior and causing the mantle to warm slightly. This warming eventually weakens the lithosphere above, making it easier for the supercontinent to break apart and for new ocean basins to open, exposing more mantle to surface cooling and allowing the system to equilibrate again. When subduction carries large volumes of water-rich sediment into the mantle, the water lowers the melting point of the surrounding rock, potentially generating more magma and more volcanic activity at the surface. When volcanic outgassing releases carbon dioxide from the mantle into the atmosphere, it warms the planet through the greenhouse effect, increasing weathering rates and eventually drawing carbon back out of the atmosphere through the formation of carbonate rocks that are then subducted and returned to the mantle. These feedbacks operate over tens or hundreds of millions of years, slow enough that they are difficult to detect in the geological record, but persistent enough that they have shaped the evolution of the planet since its formation. There is something paradoxical about knowing with confidence the conditions inside a place you can never visit. We speak of pressures of 3 million atmospheres at the center of the Earth, as if this were a measured quantity, as if someone had placed a gauge there and read the value directly. But of course, no one has, and no one will. The number comes from calculation, from integrating the gravitational acceleration through successive shells of material whose density we infer from seismic wave velocities, which themselves are measured by instruments on the surface that detect vibrations lasting a few seconds or minutes, vibrations created by earthquakes that release energy accumulated over decades or centuries along fault lines in the crust. The chain of inference is long and indirect, and yet the result is reliable enough that geophysicists around the world agree on the pressure at the center to within a few percent, which is remarkable given that the quantity being estimated is so far beyond direct measurement. This reliability comes from redundancy, from the fact that multiple independent methods converge on the same answer. Seismic waves tell us the density profile of the Earth, and from density, we can calculate pressure if we know how materials compress under load. Laboratory experiments tell us how iron and silicate minerals behave at high pressures and temperatures, and these data allow us to predict which minerals should be stable at which depths. Theoretical models based on quantum mechanics tell us how atoms interact when squeezed together, and these models can be tested against laboratory data and then extrapolated to conditions beyond what laboratories can achieve. When all three approaches, observation, experiment, and theory, agree, we can be reasonably certain that we understand what is happening, even if we cannot observe it directly. This is the nature of scientific knowledge at the limits of accessibility. It is built from convergence, from the mutual consistency of different lines of evidence, from the elimination of alternatives that do not fit the data. But there is still an element of abstraction in this knowledge, a sense in which the pressure at the center of the Earth is more of a mathematical construct than a tangible reality. You cannot feel 3 million atmospheres. You cannot imagine what it would be like to experience it, because no sensory apparatus could survive long enough to transmit information about the experience. The pressure is real. It has measurable consequences. It shapes the structure of the planet. It determines which materials exist at which depths. But it is real in the way that very large numbers are real, or very long timescales, or very small distances. It is a quantity that exists beyond the scale of direct human perception, accessible only through instruments and calculations that translate the remote into the representable, the unimaginable into numbers that can be written down and compared and used to make predictions. This does not make the knowledge any less valid, but it does mean that our understanding of the deep earth is fundamentally different from our understanding of things we can see and touch and manipulate. When you hold a rock in your hand, you know its weight, its texture, its temperature. You know it in a direct, immediate way that requires no instruments, no calculations, no models. But the rock at the center of the earth is known only through abstraction, through the application of physical laws to conditions that have been inferred rather than observed. The rock at the center is iron, we say, compressed to 13 grams per cubic centimeter, heated to 6,000 degrees Celsius, held in a hexagonal, close-packed crystal structure by pressures exceeding 3,600,000 atmospheres. All of this is true, or as close to true as current knowledge allows, but it is a different kind of truth than the weight of the stone in your hand. It is mediated truth, constructed from theory and data, and the assumption that the laws of physics apply everywhere, even in places we cannot reach. And yet this mediated truth is powerful. It allows us to predict how the Earth will evolve over billions of years, to understand why the magnetic field exists and how it might change, to explain why earthquakes occur where they do, and why volcanoes erupt where they do. It allows us to compare Earth with other planets, and to understand why some have magnetic fields and others do not, why some are tectonically active and others are dead. It allows us to reconstruct the history of the solar system, to infer the conditions under which planets formed, to estimate the abundance of different elements in the cosmos. All of this comes from understanding pressure, from knowing how matter behaves when compressed, from recognizing that the interior of a planet is shaped by the cumulative weight of everything above it, and that this weight creates conditions that have no analog at the surface. The pressure at the center of the Earth is not mysterious in the sense of being unknown or unknowable. It is mysterious only in the sense that it represents a state of matter so extreme that we have no intuitive grasp of it, no everyday experience to compare it to, no way to visualize what it would be like except through analogy and approximation. Pressure in the deep earth is patient in a way that nothing at the surface can be. It does not fluctuate with seasons or weather. It does not respond to daily cycles or tidal forces, except in the most negligible ways. It simply persists, unchanging across timescales that dwarf the entire history of human civilization. The same pressure that exists at the core mantle boundary today existed there 100 million years ago when dinosaurs walked the surface, and it will exist there 100 million years from now when whatever species then inhabits the planet looks back at our era as we look back at the Cretaceous. This constancy is not the result of careful maintenance or active regulation. It is simply what happens when gravity acts on a sphere of rock and metal, when mass accumulates and compresses itself under its own weight, when the only way for pressure to change would be for the planet itself to lose or gain significant mass. And that does not happen except over timescales measured in billions of years, timescales comparable to the age of the solar system itself. We live in the thinnest possible layer, where pressure is low enough for complex chemistry to occur freely, where water can exist as a liquid, where carbon can form the long chains and complex molecules that underpin biology. This layer is only a few kilometers thick if you measure it by the depth at which pressure begins to inhibit the kinds of reactions that cells depend on, only a few tens of kilometers if you measure it by the depth at which rock becomes plastic and starts to flow. Below this, the conditions are inhospitable, not because they are toxic or caustic, but simply because they are too confined, because the pressure squeezes everything into forms that cannot support the disorder and flexibility that life requires. Life is a surface phenomenon not by accident, but by necessity. constrained to the thin shell where pressure is low enough to permit the constant assembly and disassembly of molecules, where atoms can move freely enough to participate in the reactions that extract energy from sunlight or chemical bonds, where structures can form and dissolve and reform without being locked permanently into place by the weight of the planet. And yet, we depend entirely on the pressure below. Without it, the mantle would not convect. Without convection, there would be no plate tectonics, no volcanic outgassing to replenish the atmosphere, no recycling of nutrients through subduction and volcanism, no mechanism to regulate the planet's temperature over geological time. The continents would not drift, mountains would not rise. The magnetic field would not exist, and without it the solar wind would slowly strip away the atmosphere, as it has done on Mars, leaving the surface exposed to radiation levels incompatible with most forms of life. The deep pressure is what makes Earth a dynamic planet rather than a static one, what prevents it from cooling into the kind of geological death that has claimed smaller rocky bodies like the Moon or Mercury. We live on the surface, but we are sustained by processes that occur thousands of kilometers below, processes driven by pressures we will never experience and temperatures we can barely imagine, processes that operate on timescales so long that they are imperceptible within a human lifetime, but which over millions of years reshape everything. There is a kind of humility in recognizing this dependence, in understanding that the surface environment we inhabit exists only because of conditions in the interior that we cannot control, cannot alter, and can barely observe. We are, in a sense, passengers on a planet whose behavior is determined by forces and processes that dwarf anything happening at the surface. The entire biosphere, every organism that has ever lived, every ecosystem that has ever existed, all the complexity and diversity of life on Earth represents an extraordinarily thin layer of activity confined to the zone where pressure is low enough to permit it. Below that zone, the planet continues for thousands of kilometers, indifferent to whether life exists above it, operating according to principles that predate the origin of life and will continue long after life, if it ends, has disappeared. This is not a bleak realization. It is simply a statement of scale, a recognition that the processes governing planetary interiors are older, larger, and more fundamental than the biological processes that fascinate us because we are part of them. Pressure, viewed from this perspective, becomes something more than a physical quantity. It becomes a boundary condition, the thing that defines what is possible and what is not, what can happen at the surface and what must remain confined to the depths. It is the reason rock melts at some depths and not others, the reason continents float on the mantle rather than sinking, the reason the core remains liquid and generates a magnetic field. It is the invisible architecture that shapes the planet, determining its structure, its behavior, its evolution over billions of years. Pressure builds silently. It does not announce itself. It accumulates grain by grain, layer by layer, across distances and timescales that make observation impossible. At the surface, you feel one atmosphere pressing evenly against your skin, and you feel nothing at all because it has always been there. A few kilometers down, the pressure doubles, then doubles again, then climbs into ranges where numbers stop meaning anything except as abstractions, as placeholders for forces that exist beyond the reach of sensation or imagination. By the time you arrive at the center, not physically because no arrival is possible, but conceptually through calculation and inference, the pressure has reached 3,600,000 atmospheres, and iron, heated to temperatures that match the surface of the sun, remains solid because it has no other choice. This is the condition we have been following downward through rock and metal, through transitions marked only by the rearrangement of atoms into tighter configurations, through regions where the material flows but never breaks, where time stretches until motion becomes theoretical. The journey is one of accumulation, of weight adding itself to weight with perfect patience, with no haste and no conclusion. Pressure does not end at the center. It simply reaches a maximum, a point where all directions are outward and the force is distributed evenly in all dimensions, a geometric fact rather than a destination. We know this place exists. We know its temperature, its density, its composition, at least approximately, at least within the margins of uncertainty that all remote knowledge carries. We know it through seismic waves that pass through it in seconds, through laboratory experiments that recreate fragments of its conditions for fractions of a second, through equations that describe how matter behaves when compressed beyond anything we will ever touch. The knowledge is real, but it is not the same as presence. The center of the Earth is as inaccessible as anything in the universe, separated from us not by distance alone, but by the material of the planet itself, by pressures and temperatures that would annihilate any probe, any instrument, any structure we could design. It will remain unknown in the direct sense, permanently remote, observable only through its effects. And perhaps this is fitting. Not everything needs to be visited to be understood. Not every place requires a witness. The deep interior operates according to principles that do not depend on observation, that were established billions of years ago and will persist billions of years into the future, indifferent to whether anyone at the surface knows they exist. Pressure continues to shape the planet whether we measure it or not, whether we think about it or not, whether we are here or not. It is one of the fundamental facts of planetary existence, as universal as gravity, as inevitable as time. The surface where we live is shaped by this depth, even though the two rarely touch directly. The ground beneath your feet is the thinnest boundary, a skin floating on an interior that extends downward into conditions we describe but do not experience. And yet the description is enough. It allows us to see in some limited but meaningful way the architecture that supports everything above it, the silent engine that has been running since the planet formed and will continue running until the sun expands and consumes the inner solar system billions of years from now. Pressure is accumulation made permanent. It is weight that does not shift, force that does not relent, confinement that shapes everything it touches into forms that can exist only under its influence. It is invisible from the surface, but it is everywhere below, increasing with every meter of descent, reaching extremes that seem impossible until you remember that they are simply the result of gravity acting on mass. Nothing more mysterious than that, nothing more extraordinary than the fact that matter occupies space, and space curves under the presence of matter, and everything falls inward toward everything else until equilibrium is reached. We have descended as far as thought allows, to the center where pressure peaks and iron remains solid, despite heat that would vaporize it anywhere else. And now, having arrived conceptually at this unreachable place, we can let the descent settle, let the knowledge rest, let the mystery remain exactly what it has always been, a place we understand without ever visiting, a condition we describe without ever experiencing, a depth that will remain deep no matter how carefully we listen to the waves that pass through it. If this journey brought you a sense of calm, you can subscribe to Quiet Science and continue exploring these silent depths with us.